A given rectangular coil OLMN of area A carrying a given current I is placed in a uniform magnetic field vector B equals B K cap in two different orientations A and B as shown. So we have figure A and B, and we have rectangular coil OLMN. Okay. So in figure B, we have rectangular coil OLMN. Okay. Of area A. So we find area in figure A and figure B is same in magnitude. Okay. And the rectangular coil OLMN is placed in a uniform magnetic field vector B. Okay. And vector B a given rectangular coil OLMN of area A carrying a given current I is placed in a uniform magnetic field vector B equals B K cap in two different orientations A and B as shown. What is the magnitude of torque experienced by this coil in the two cases? So we have rectangular coil OLMN, okay, in figure A and figure B, and the area of the coil is A in magnitude, and the coil is carrying current I. So we can see the direction of current is anti-clock, okay, in figure A, whereas direction of current in figure B is in clockwise direction, and the rectangular coil is placed in a uniform magnetic field vector B, okay, acting along positive Z axis, because we have vector B equals magnitude of B, that is magnetic field, times unit vector K cap acting along positive Z axis. So we have magnetic field, okay, in both the figure or diagram acting along positive Z axis. Now we are asked to determine the magnitude of torque experienced by this coil in the two cases. So we are going to use the concept of torque experienced by current carrying coil placed in magnetic field. So I'm writing, okay, torque experienced by current carrying coil placed in magnetic field is torque tau equals vector M cross magnetic field B. So we have this expression for torque, okay, clear? So this is torque, and vector M, it is magnetic moment of the loop, or it is also called, okay, so I'm writing over here, it is also called magnetic dipole, okay, moment of the loop. And for loop, okay, for current carrying loop, vector M equals N I vector A. So N, okay, this represent number of turn or turns, and in figure A and B we have n equals 1. So we have this, and I represent current, and vector A represent area of the loop, and vector area equals magnitude of area times n cap. Okay, so we have this where n cap, okay, this is unit normal drawn on the loop. So we have this. So we are going to use this expression for torque, okay, in figure A and B. Now, let us understand this problem with reference to these two figures drawn, okay. So we can see we have rectangular coil, okay, in this orientation, and we have rectangular coil in this orientation. That is, we have rectangular coil, okay, in orientation A and B. So I have represented the orientation of rectangular coil in this way. So we have this. So I'm showing the faces of the coil, okay. Now, when we consider this figure, okay, what we find when we observe from this side, okay, because this is the front face. So this is the front face, and the face opposite to the front is at the back side, okay. So this is the opposite or back face, okay. So when we observe from this side, when we observe from positive x-axis, okay, we can view this face only. And what we find, the area, okay, for this face, the area vector is acting along positive x-axis. Clear? It means that the unit normal on this face is acting along positive x-axis. So we can represent, okay, area vector in figure A in this way, okay. Vector area equals magnitude of area times unit vector I cap acting along positive x-axis. So we have this. Okay. Now, when we observe rectangular coil, okay, in this way, we are observing rectangular coil, okay, vertically down, then we can observe this upper face, okay. So this is the upper face, okay, and we have opposite or bottom face, okay, acting, or let me write in this way, bottom face facing downward. Clear? So in this case, opposite or back face is facing along negative x-axis. So we have this. So we need to understand this, okay. And we have front face, okay, it is facing along positive x-axis. So we have this positive x-axis. So we have this. So this is to be noted, okay. And we can see upper face is facing along positive z-axis. Okay. It means that area vector of this upper face, it is acting along positive z-axis. It means that the unit normal, okay, the unit normal acting on the upper face is directed toward positive z-axis. So for figure B, okay, we find vector area, okay, of the upper face equals magnitude of area A times unit vector, okay, acting along z-axis. So we have this, and unit vector acting along z-axis is k cap. So we have this. Now, as I said earlier, okay, we are going to use this expression for torque, okay, in figure A and B, okay. So we have torque tau equals magnetic dipole moment, okay, vector M cross magnetic field, and we know magnetic dipole moment or magnetic moment of coil equals number of turns and, okay, current, and we have vector A, that is area vector. So we have this, and in both cases, okay, we have number of turns n equals 1. So we have this number of turns n equals 1. Okay, we have this. So we can see in these two figures, okay, I have made a rectangular coil, which is, we can see it is thick, but actually, okay, we have a single turns, okay. So I'm drawing thick just to know or get the idea of two opposite faces, okay. Now what we do, torque tau equals n I area vector cross magnetic field. So we have this expression, okay. So let us call it equation 1. Now we are going to use equation 1, okay. So using equation 1 for figure A, okay. So we can write torque tau equals n, and n is 1, okay. We have this. So 1 times I. So we can see current I is flowing, okay, in this direction. It is flowing in anti-clockwise direction, whereas in this case, okay, the coil is horizontal, and we find current I flowing in clockwise direction. So we have this. So I, and we have area vector, okay, acting along positive z-axis. So we have A I cap cross magnetic field, and we have magnetic field acting along positive z-axis. So I'm writing in this way, B K cap. So we have torque tau equals I A B, and we have I cap cross K cap. Now we know, okay, when we have this, okay, I cap cross J cap, then we get K cap, okay. And when we have this, okay, J cap cross K cap, then we get I cap. And when we have K cap cross I cap, yeah, we get J cap. So this is to be noted, okay. Now we can see we have I cap cross K cap. So this gives me, okay, this cross product gives me minus J cap. Therefore we can write torque tau equals B IA, and we have minus J cap. So it indicates that, okay, the direction of torque, okay, the direction of torque in this case or in this figure, okay, is acting along minus, it is acting along negative y-axis, because we have minus J cap, okay, because we know unit vector along positive y-axis is J cap and unit vector along negative y-axis, okay. So this is minus J cap. So what we find, this is along negative y axis. So we have this. Clear? Now we are going to use equation 1 for figure B. Clear? So torque tau equals, number of turn is 1. So we have 1 times I, and area vector, okay, is acting along positive Z axis. So we have A K cap cross magnetic field, okay, is acting along positive Z axis. So we have B K cap, okay. So we can write in this way, okay, IAB, and we have K cap cross K cap. So we have this, and we know this cross product is 0 because we have I cap dot I cap equals 1, J cap dot J cap equals 1, sorry, and K cap dot K cap equals 1, but I cap cross I cap equals 0. Same way, okay, we have this J cap cross J cap equals 0 and K cap cross K cap equals 0. So we are using, okay, this, okay, concept. Therefore torque, okay, in this case this is 0, okay. So we have this. Clear? So this is to be noted. Now the magnitude of torque, okay, so we are asked to find. So from question, okay, we are asked to find magnitude of torque. Therefore in this case, okay, the magnitude of torque tau equals BIA, and in this case the magnitude of torque equals 0. So we have this. Okay, so we have this.